Hi everyone, we're going to crunch down one book chapter into one lesson. Lesson 39, Hypothesis Test for Two Populations. How do we compare two populations? Now, this is a really big topic, but my feeling is that if you understand the philosophy of one population or one sample hypothesis test, then you should be able to extend these ideas to this lesson and you should be able to pick this stuff up. I don't want to bore you with additional details when the key is really the fundamental philosophy of hypothesis testing, and we've done that. Part A, means from dependent samples, matched pairs. So, for example, let's take a look at this picture here, right? Now, we don't have 6 completely independent members here of the population, okay? We have here matched pairs. Let's say from here to here, from here to here, and from here to here. Maybe each blue-red pair is an individual. Maybe blue is a before measure, red is an after measure. Or maybe we have the same measures for a husband-wife couple. It could be a couples therapy program where they take a test and you have the husband score and the wife score. Husband score, wife score, husband score, wife score. So here, we might be interested in comparing the means for the two measures, whether it's the before measures and the after measures, or the husband's measures and the wife's measures. And the idea is that for each of these individual pairs, which could correspond to an individual that we're getting before-after measures on, or maybe each of these pairs is a couple, it's a pair, a husband-wife pair. The idea is that we take the differences for these pairs, right? Whether it's before versus after, husband versus wife. That sounds like a great game show, husband versus wife, Family Feud. All right. But the idea is that with D here, all right, we're going to find the differences between these measures for each pair. Okay, these are matched pairs, right? These two are matched. Each blue dot and each red dot is matched. It's like a couple or different measures for the same individual. And the idea is that we're going to perform a t-test on these differences. Before, like if we're looking at the heights of a bunch of students in a class, right? We list a bunch of heights. We can take a sample mean, sample standard deviation, and do a t-test. Over here, we're going to do a similar analysis for the differences. So in a sense, it is kind of a one population, one sample problem, although it's a population of differences though, which is kind of weird. It's a population of differences. The population data. Let D be the distribution of the population of differences between all the matched pairs. Not the raw heights for the various students, okay, but the differences within each couple, within each pair. Now, the thing that we want to estimate, the thing we're aiming for, we want to test for the population mean of the differences, mu sub D. That's the mean of the D distribution, the distribution of differences. So based on the sample data, we're going to get the sample mean difference, D bar, kind of like X bar, except for differences, and S sub D, which is the sample standard deviation for the differences. N is the number of matched pairs. So over here, N would not be 6, N would be 3. We have 3 pairs. Okay, the Clt assumptions as usual. Let's go straight to an example. We take a random sample of 3 men from the participants in a men's weight loss program. Use the sample data below to test the claim that, okay, so here's the claim. I'll put this in red. Test the claim that participants in the program lose weight on average. That's our claim. I'll start. Use a significance level of 0.05, our average. That's going to be our what? That's going to be our value for alpha, the significance level, 0.05, the usual. Assume that the weight changes of the participants in the program are approximately normally distributed. So the CLT applies. So let's say we have these 3 men. We have a before weight and an after weight in pounds. We want to know if participants in the program lose weight on average. That's the claim. Solution. First of all, calculate the differences from the table, and you have a choice. You can either take the differences before minus after, or after minus before. Actually, in calculus, you normally do it after minus before. But here we're going to do it before minus after. The idea being that if we have a bigger positive number, that indicates a greater weight gain, which in a way would be the more positive result if you're producing a weight loss pill. Let's ignore the side effects for now, okay? Runny nose or who knows what, right? But let's say that weight loss is good in the sense that you're producing a weight loss pill. Okay, so for example, here, this person number one, man number one, has lost 5 pounds. Here, man number two has lost 2 pounds. And over here, man number three actually gained a pound. Still, it's possible that the weight loss pill might be effective for weight loss, but perhaps this person got unlucky in that regard. Maybe, in a sense, this is sampling error, which may not mean much to person number three. Well, whatever. I mean, I didn't like this pill. Okay. Anyway, sample statistics. N equals 3. That's the number of matched pairs. Each matched pair consists of a before weight and an after weight for one man. Okay. Here's the sample mean. If you work out the sample mean for this D column, right, it's going to be 2.0 pounds. Remember, we go to 1 decimal place further. The sample standard deviation is 3.0 pounds. You can get that from a calculator or Excel. The setup. Now, the claim is that participants will lose weight on average. A weight loss corresponds to a positive difference, okay? A positive difference if you go before minus after. So here, the claim is the alternative. The claim is the alternative, which says that mu d will be greater than 0. It's a right-tailed test. Remember, we write the null as mu sub d equals 0, although it technically includes other cases as well. Alpha is 0.05. Now, bear in mind that, again, a positive value for mu sub d corresponds to weight loss on average. But if we had taken the differences after minus before, then this would have been a left-tailed test. And basically, you'd get an equivalent result. Basically, your claim will be equivalent in either case. Your conclusion will be equivalent in either case if you're using the same claim. So you could do either. You could either set it up as before minus after, in which case we have a right-tailed test here, or you could set up the differences as being after minus before, in which case it would be a left-tailed test. Either is fine. Just be consistent. Okay, the methods of the lesson apply for the usual reasons, like for the t-test, except we're looking at differences. We're doing a t-test on differences. Here's our t-test statistic. The mean sample difference minus, or the mean of the sample mean of the differences. D bar here. Sample mean of the differences between the matched pairs, okay? Minus the mean of the differences under the null. Now remember, the null said that mu sub d was equal to 0 pounds. It was the borderline case of all that, okay? We're going to assume mu sub d is 0 pounds, which means this part of the formula goes bye-bye. That's often the case. The upper right goes bye-bye. 0. Over, it's like the CLT thing, right? The sample standard deviation of the differences over root n. Plug in, careful, it's a compound fraction. You get about 1.155, a t-test score, a t-test statistic. Now, using the traditional method, you could use the p-value method, but using the traditional or classical method, you can find the critical value that's involved, a t-distribution on n-1 or 2 degrees of freedom. Alpha is 0.05. It's a right-tailed test. Turns out 2.920 is the CV. It's a right-tailed test. Now, is the test T in the critical region or not? It is not. It is not. So it does not fall in the danger zone, the acid bath regarding the null. Remember, the null dies here. The null dies in the critical region. Here, the null does not die. All right. The test statistic value, the t-test score, is not in the critical region, so we do not reject the null. Is that strong or weak? That's weak. I sound like Cartman from South Park. That's weak. There is insufficient evidence. What? The alternative is the claim. It's like a research hypothesis. It's like we're researchers for this drug company that's producing this weight loss pill. We're claiming that our research hypothesis is true, that this pill works, right? So we're weighing evidence for or in support of the claim. But there's insufficient evidence for or in support of the claim that participants in the program lose weight on average. That's our claim star. So if the drug company claims, on average, our weight loss pill works, based on this statistical hypothesis test, there's insufficient evidence. Maybe it does work, but we don't have enough evidence. Next time, what about comparing means from independent samples, like men versus women who are single, so they have nothing to do with each other right now? That's next time.